Welcome to The Explainer. Today, we're diving into a really fascinating evolutionary journey. We're going to map out the exact path of modern artificial intelligence, tracing how the tools and tech have evolved from absolute basics to the incredible digital landscape we're all navigating right now. So if you've ever wondered how the ground floor building blocks of data science actually stack up to create today's cutting-edge AI, well, you're in exactly the right place. Let's get into it.
Because really it all boils down to this one pretty incredible question. How do you actually go from a completely blank screen to a fully autonomous AI agent? I mean, it doesn't just happen by magic, right? It's a structured, hands-on climb from basic data fundamentals all the way up to complex, self-directed systems.
And here is our roadmap for that climb. 1. Foundation data and Python. 2. Machine learning and big data. 3. Deep learning and vision. 4. Generative AI and RAG. And finally, number 5, the age of agentic AI.
Okay, let's dive into this. Section 1, Foundation, Data, and Python.
You know, the starting point for every data scientist is actually pretty humble. It all begins with mastering Python in a Jupyter notebook, staring at a totally blank script. It's where you learn the absolute essentials, like how to wrangle variables, write loops, and organize messy information into neat lists and dictionaries. It's less Terminator and more digital housekeeping, but it is the absolutely essential first step.
But obviously, raw Python just isn't enough for the sheer volume of data out there. Before any true machine learning can actually happen, we have to prep the data. Think of NumPy as your heavy-duty calculator for multidimensional arrays. Then you've got Pandas, which is basically your superpowered spreadsheet for grouping and merging. And Matplotlib? That allows you to paint a visual picture with the data, turning endless boring rows into really clear scatterplots and charts.
Moving right along, Section 2, Machine Learning and Big Data.
Now what's really interesting here is how we start teaching machines to actually find patterns. We essentially use two main branches of learning. In supervised learning, we act as the teacher. We guide the machine with clearly labeled data to predict outcomes using algorithms like random forests. But in unsupervised learning, the machine is totally on its own. It explores unlabeled data to find hidden structures, using clustering techniques like k-means, to build things like, say, the recommender systems that suggest your next movie to watch.
But look, building a smart model is literally only half the battle. The really crucial part is how we practically maintain these models out in the real world. And that brings us to a vital concept, MLOps, or machine learning operations. Think of it as continuous integration and deployment specifically tailored for ML. It covers tracking experiments with tools like MLflow and monitoring models so they don't experience model drift or lose accuracy over time. Because, let's face it, a model that perfectly predicts yesterday's trends is totally useless tomorrow.
So what happens when real-world datasets become just way too massive for a single computer to handle? Well, that's exactly when we bring in PySpark. By utilizing Apache Spark's architecture, PySpark allows for in-memory computing and distributed big data processing across multiple machines. To put that into perspective, it's basically the difference between trying to empty a giant swimming pool with a plastic bucket versus using an industrial pump.
Stepping up the ladder, Section 3, Deep Learning and Vision.
Now, machine abilities didn't just happen overnight. They evolved in phases. Generation 1 gave us perceptrons, those foundational simple nodes. Then, Generation 2 introduced CNNs, which really unlocked the power of image classification. Generation 3 brought us RNNs, allowing machines to finally process sequences of data. But Generation 4? That was a massive breakthrough. LSTMs, or long short-term memory networks, introduced memory gates. This gave the machine the vital context it needed to actually remember past sequences of information.
And teaching these neural architectures to process human language? Yeah, that's incredibly complex. Natural language processing, or NLP, involves breaking down our very messy, unstructured text. Through techniques like tokenization and tagging parts of speech, we essentially teach the machine the grammar and syntax of our world, which finally allows it to mine plain text for real meaning.
But keep in mind, this isn't just abstract theory happening in some research lab. Deep learning operates right in our daily reality. For example, OpenCV is the computer vision framework that processes images to build face detection apps. This is exactly the kind of technology powering the systems you probably use on your smartphone every single day to unlock your screen.
Next up, Section 4, Generative AI and RAG.
Okay, this is where things get really wild. With these massive pre-trained large language models, the LLMs we hear so much about, the challenge completely changes. We aren't just writing code anymore, we are actively guiding behavior. And this introduces the critical art of prompt engineering. To get reliable outputs, we have to instruct these models using really precise strategies. We're talking everything from zero-shot prompting to providing a few examples with few-shot prompting, all the way to advanced chain-of-thought strategies that literally force the AI to reason out loud step by step.
But here's the catch, right? Even the absolute best prompt in the world cannot force an AI to just know your private enterprise data or recent events it wasn't originally trained on. And that brings us to RAG, Retriever Augmented Generation. Let's demystify how we actually give AI an external, searchable memory. Step 1, we convert our private documents into numbers using embedding models. Step 2, we store those embeddings in specialized vector databases like ChromaDB or Pinecone. Step 3, when a user asks a question, we use a hybrid search to retrieve the most relevant documents to augment the context. And finally, Step 4, we feed those specific documents straight to our LLM generator, which formulates a highly accurate, context-aware answer.
And this brilliantly illustrates the true power of that architecture when mapped out end to end. We aren't just relying on what an AI memorized a year ago. Instead, we are actively hijacking its reasoning engine, inserting our own custom, retrieved data right before it generates its answer. This pipeline right here, this is the absolute secret sauce behind almost every single modern, customized enterprise AI application today.
Which leads us to our final stop, Section 5, the age of agentic AI.
We are rapidly moving toward this futuristic vision of autonomous multi-agent systems, where machines use collaborative frameworks to delegate tasks and solve super complex problems entirely on their own. But the practical reality of managing them isn't quite sci-fi just yet. It's an LLM Ops fine-tuning dashboard. These agents require really rigorous monitoring and evaluation to ensure they don't, completely go off the rails. So, to deploy these systems securely in a real enterprise, you need a finalized, heavy-duty stack. Agentic frameworks like LangGraph, AutoGen, or FiData basically orchestrate the AI workforce. Then, advanced LLM Ops tools like PEFT and LoRa allow you to fine-tune massive models super efficiently. You're essentially tweaking the AI's brain without having to rebuild the whole thing from scratch. Combine that with multimodal apps, seamlessly blending text, vision APIs like GPT-4V, and routing it all through frameworks like FastAPI, well, then you have a truly production-grade system. So, we've climbed from staring at a completely blank Python script all the way up to autonomous, multi-agent systems orchestrating complex workflows. Which leaves us with one final, absolutely essential question. As this AI landscape continues to evolve and reshape the future, where do you fit into this newly built world? What part of this massive stack are you going to master next? Keep exploring, keep learning, and I'll catch you in the next explainer.